There we go. Okay. All right. So, hi, my name is Sasha, and I'm going to be doing my particular honors project about coefficients of friction, and more specifically, kinetic friction. So I'm here with Professor Dave Havig at part of 151 for physics honors. Yeah. All right. So basically, the whole idea that kind of came across when I was thinking of my entire honors project. Well, originally I wanted to do something else, but I couldn't figure out how to make it work. And so now I'm doing friction instead. So with that, basically the idea was to not try and rely on coefficients that you find online, not trying to look things up and trying to calculate them like you might do when you don't have the internet. And so what I was able to do is basically I designed an entire, basically like a ramp. And through that, I was able to pretty much have a wooden puck move from point A to point B. And it basically, through that entire process, I recorded it using a particular software that we'll talk about in a second. And then I also, using that software, was able to mark and pinpoint different locations that could give me a very accurate reading and kind of basically help me figure out what the velocity was and the time interval it took and everything like that when it gets to point A and point B. And then along with that, to kind of figure out force as well, because I wanted to use two different techniques to find kinetic friction, and more specifically that coefficient. I also put a stationary object on the right side at the end. And there's a little bit of a change in that particular pan, and we'll also go over that in a little bit as well, because it's not supposed to be a square. And I figured that out like halfway through the project. So yeah, like every single experiment, things change. Anyway, so the materials I kind of made for this was going to be, there's a plank of wood. So I wanted to try 3 different structures. So 3 different, basically ramps that they can use to test different friction coefficients instead. So I used a mirror, which basically is very similar to glass. So that's what I used for that. I also used a nice acrylic sheet, which if you can see, there we go. Right here is kind of laying on top of that wooden plank that I have, which is the 3rd one. And now the reason I did that was because the sheet on its own, as you guys can also see, is very, very thin. It would bellow. And you wanted it as flat as possible. And so that way it wasn't affecting the way that it what basically went across the board. Now at the bottom, you can also see my nice wooden puck, which is basically the leg of a couch that I bought from Lowe's and maybe might be returning. And then also the mirror over here as well. So the mirror is considerably longer than the rest of it. So I did have to account for that, especially when I was doing my calculations. And I did attempt to start and stop each point at the same exact time. So right here to right here. And there's a nice little divot in the ground as well that basically allowed me to do that and just basically keep everything the same angle and the same length as well. So other than that, Capstone software. So Capstone, basically what it is software that you have on your computer that helps to, if you are recording things as well, or other different data analysis that you might be using, is a way to more accurately do that, other than say timing and stopping and things like that using a stopwatch. Sometimes your reaction time can be a little slow. And so to make sure that I was getting the best and precise kinds of measurements and data, I wanted to use Capstone instead. And we'll go over and look over what that looks like on a screen, because I do have a screenshot of that I put up here. Okay, so the plan, like I mentioned, so we're going to do 3 different trials of this with 3 different sheets. We're doing the wood, we're doing the acrylic, and then we're also going to be doing the mirror as well. And so the idea was, again, we're looking only at kinetic friction. We're not looking at static, because static, basically what that is the friction that keeps something still on that particular ramp. Now we wanted to look at it moving. And so with that, we're only looking at kinetic friction, because that's when it's moving, it changes from static to kinetic. All right, so when calculating the force, like I mentioned earlier, it's going to be, we're looking a little bit more at that stationary object rather than everything else. So once this leaves the area, it's going to be hitting that stationary object. And I measured that push force that it did and how that motion transferred to that stationary object. Now, the one issue with this is the square. So it's a cube. And the thing is that when it's a cube, it has its own friction. And so trying not to calculate that and not having to look that up compared to the concrete on the ground to the cube itself, I changed it from a cube to a sphere, because that way it rolls and there's no friction. Well, there's considerably less friction. Experimental phase. Yeah, so with this, basically what the testing is, and there's no videos. Basically what it is the, basically every single ramp was at about a 44 centimeter height. So I used a meter stick to kind of basically map everything out. And then throughout each individual trial, as we can see, the acrylic is about 2.4 seconds. So that one was about midway. So the wood took a little bit shorter. And then the mirror itself took a very long time. It took 6 minutes. And so I left the camera running. And when I got back from eating my dinner, I eat dinner really quickly. It was still going. And so that one, unfortunately, caused a little bit of trouble when it came to stationary objects, because it wouldn't push it, because at the end of the ramp, it just stayed still because it had no energy left. So with that, and there's no real reason to be specific with degrees. Now, the original plan was that every single one was going to have about 30 degrees for an incline. However, because they're being calculated all differently, I didn't need to do that. So each one is still at the 26.1, it's changed. But it didn't need to be that specific. So that's just something that happened. And then lastly, the weight of that particular puck that I had is 0.363 kilograms. Oh, yay. Okay, well, this works somehow. Let's see if they work. Okay, no, they don't. But that's what that looks like, basically. So I had a meter stick here. I have a laser pointer. And so basically what happened was that I measured it from here to here using that capstone project. And basically how I know about capstone is because we do it in labs. And so we do it in our physics class. And I was just trying to replicate that as much as I possibly could in terms of that entire lab itself. So this was the wood down here and then the acrylics up here. I did not put in the 6-minute video because that would have taken way too long. Okay, so when mapping that out and when calculating that all, basically I didn't use the regular axis you might consider, especially like in a math class where it's going to be straight up and down and side to side. Instead, I tilted it. And that's because you don't have to use this many calculations to figure out everything, and it makes it a lot more simple. Basically, I was only working with that x-axis, and so it made it a lot more simple not to have to do a lot of trig to figure out everything in a lot of different angles. Now, what we were using for equations, we were using the kinetic friction. So you're going to have your coefficient. So that's the, again, up top. It basically, if you've ever seen that symbol, it looks very much like a U. I didn't know how to put symbols on here. And then your normal force as well. But everything, again, considering that it is quite the structure right here, everything's going to be angled. So you're going to have to use sine and cosine to figure that out later on in your calculations. Other than that, because we're also using gravity, we're also using forces as well. We have our max for static friction, which again, we're not using, but we also have the weight being mass times force gravity because we're on Earth. And then again, the entire force that we're using later on, that entire chunk equation we have right here is going to be the total acceleration of the system, not just this, which it technically is still a system, and then the mass of that, and then the force of gravity, you know, always going to be tilted on that axis to find it eventually, and then the force of friction, same thing, because the normal force is going to be tilted as well. And then that's the software I was using. So these X's and these entire yellow lines that we see right here are all from Capstone. So it's all something that I did on my computer, and they were able to pretty much map that out. And as you guys can see, as these X's get a little bit further apart, it's actually speeding up because it's the same time interval. Okay, so force of an object in motion. That's the one tricky part with the sphere. I used a tennis ball, it didn't work. And so I didn't have any calculations for it. And I tried very, very hard to do that. And I apparently don't know how to spell anything anymore. But with that, so the collision was going to be an elastic collision between the wood puck and the tennis ball. And for two of them, it worked. And it worked very, very well. However, with the glass that I had, it wasn't enough to push the tennis ball, which is very, very sad for that puck. But that means I couldn't really calculate it, especially when it comes across all three trials. So I didn't end up doing the calculations for those. I did have a video on it. Let's see if it actually shows up so that you can see what that kind of looks like. It's not most likely going to play, but you're going to be able to see that the tennis ball here, again, is going to be placed right next to it. That way the puck doesn't have time to slow down and to hit the floor and to act with friction. But basically what happened is, especially with the wood, because it was indeed fast enough to push that tennis ball, what happened was that it came down the ramp, it hit tennis ball, the tennis ball went flying, and then the puck just stayed here. And so it lost all of its motion, most likely because it hit the ground and not necessarily the tennis ball, because it still slightly moved afterwards. It's just the friction due to the ground was a little bit too much for it. So my results, I did calculate using, again, the acceleration from capstone instead. Like I mentioned, I was going to do 2 different methods. This is the first method. So all those calculations, as you guys can see right here, that I did basically the first one. So the wood on wood was about 45.45 as the coefficient. And then all the way to the expected values, which were what I looked up to kind of compare my method, was 0.05. So it wasn't that far off, which is really, really good because it looks like my method is going to work out very well. Same with the wood on plastic. You know, we have 0.34 compared to a 0.4 as well. Very, very similar again. And the change in time and the change in position were all things that I got from capstone. However, with the wood on glass, it liked to be mean to me. And so I had a 0.49 for my calculations and a 0.02. 0.2, there we go, for this trial instead. Now, that leads me to believe, one, that I might not have gotten the correct coefficient for this particular one online, because it doesn't make sense for the rest of it. Now, if we're looking at I know you guys didn't get to see the videos, but the wood on glass is really, really slow, which means it's going to have the highest coefficient friction, because that friction is going to be more effective on it compared to the least amount, which again, didn't make sense based on what I saw in my experiment. And then I calculated percent error to be able to figure out if my method was actually truly accurate. And so because they're quite small numbers, they're going to get quite big in terms of your percent errors at the end of it. You know, we're always using this lovely percent error, which I'm sure we're all familiar with. But then the wood on glass, again, is going to be that 145% error. So obviously there's some stuff that I need to look up and to figure out whether or not that's truly accurate, because something tells me it's not. I don't know if you guys can notice either what that means, but again, wood and plastic, not so far off, which is something I am happy with. So that is technically the end of my presentation. Obviously, there's things that I can improve on. I definitely want to continue working on the tennis ball aspect of it. Maybe potentially even changing the entire thing and making it a guided ramp to make it a little bit easier to see that motion move in one direction rather than in degrees. Because if that puck hits it differently in a different angle, it's going to go in a completely different direction. And so that's also something I needed to think about further down the line. So again, these are my references, especially when it comes to finding those coefficients online and comparing them. And then also my lab as well that I used to figure out and remember how to use capstone, because it had been a minute. Again, thank you guys very much. If you guys have any questions, I'm here now. Yeah.
So I just had a question about the glass, because that is very surprising, especially considering like wood, plastic, glass. You kind of would expect a low coefficient for the glass. It's supposed to be very smooth. So do you think maybe there may have been, I don't know if you accounted for this in your experiment, but did you like clean the glass beforehand? Okay.
Yeah, I had to dig out a mirror from my garage, so I had to clean it all. It was dusty.
So did you see like any abrasions, maybe scratches on it or anything?
No, it was a relatively new mirror that we just didn't need. So it was tucked away in the garage, but I cleaned it all off. I actually even polished it a little bit because I wanted to make it as simple as possible. And it still was very, very slow. And it was very, very surprising. That was one aspect that was incredibly interesting because I wasn't predicting that.
Do you think the wood was like sticking to the polish?
I think the wood, just the grooves just weren't working very well with the glass. But basically one thing that I also found was that in order to place the puck on, you had to place it completely on the ramp beforehand. Like you couldn't have it half off, half on, like you might see with like a roller coaster by chance. It wouldn't move. Like, so that's what happened with the wood as well. It's like I originally placed it on halfway up on the ramp and halfway like not on the ramp, and it would move. So I thought that was interesting. Well, it's depending on the surface area, you can get a completely different reaction in motion and things like that.
So I had a question about the wood ramp and the wood puck, or there's just completely untreated woods and smooth there?
Yeah, completely untreated. Basically it needed to be, they were things that you could get from Lowe's, so you just pick up random scraps and stuff like that that you usually stain on your own and polish and just clean up everything like that. And then the plank that I got as well, very untreated. And same plank that I actually used to build my desk a long time ago. So I definitely know that those are untreated because my desk is falling apart.
For comments? So although there were technical difficulties, I think you handled it really well and didn't really let it phase you and just kept it although there weren't videos just explaining it, I thought you did very well and it was very thorough.
Thank you.